And rather wasting too much time, I think we should invite our next speaker, right? Prasant
Yes.
from Cisco.
Yeah. So I've joined, but I need to get the control so that I can present the TS.
Yes, no, you have been made. Hi, Prashant. I'm
Hi,
Dr.
hi.
Raghu.
Hi,
Yeah,
Dr.
welcome to
Please.
talk. We have already made you presenter. Uh, with what credentials have you logged in? You have logged in with the IIT BHU credentials?
No, I was sent a mail by Rajesh, and I just clicked the link and came here.
Right.
Good morning, everyone. So this talk is all about time-sensitive networking, which will be covered by Prasant Anand. So let me introduce Prasant Anand. Prasant Anand is a distinguished engineer working in MIG Group, Cisco system. He started his career with the Bhabha Atomic Research Center, BAR, around 27 years back. He has worked in many startup and tier-half equipment vendor and semiconductor companies like Motorola, Intel, Jupiter, Ericsson, and Cisco. His significant contributions are in carrier class Ethernet switching, for example L2, L3, data center fabric design, SDN, natural NFV, mobile service chaining, cloud SDN, virtual home gateway, cloud CPE, and enterprise gateway, multi-layer packet optic TNC, SDN, OpenFlow, Cloud LB, Smart Service Router, including security services as well as L4 to L7 session control services. He is currently driving Cisco's leadership in 5G as well. Thank you so much, Anand. Please go ahead. Now, the stage is yours.
Okay, thank you very much. So, okay, so next slide. Yeah. So this is the agenda for today. So we'll cover the reference information that will give little bit background about the conventional networking. See, TSN is all about giving certain performance level to the network traffic or network flow. So we'll see some reference information about the conventional networking, right? And what are the problems which will be fixed by the TSN. This is more, in my view, that is the most important part of this presentation. It is important to understand that what was missing in the conventional networking and how TSN has fixed it, right? So understanding problem is more important. Then what was the challenge with the Ethernet that we could not meet the traffic SLA for critical communication? And then how we are trying to enhance the Ethernet with the TSN. Some use case, very short connection between the 5G, TSN, and URLC. We hear a lot about 5G nowadays, right? And more than 5G, it's ultra reliable, low latency services, which is basically filling multiple innovative use cases like Industry 4.0, V2X, and many other low latency applications. And then we'll see in a little bit detail the three important and most important part of the TSN, that time synchronization, frame preemption, and time aware saver. And we'll at the last we'll see some other methods of the TSN which are leveraged from the conventional networking, not so much related with the TSN, but overall TSN is a basically collections of method, right? And you need to apply few methods to get certain performance level, right? So some other methods we'll see in little short, and then at the end we'll just present the centralized controller, like how end-to-end flow is set up if we want to have a critical KPIs for certain flows. What is expected is basic knowledge of L2, L3 forwarding, time synchronization, and traffic management from the conventional network perspective. And I have taken a lot of reference from the IEEE, TSN, and ABB specifications and ITUT documents. So credit goes there. Can we move to next slide, sir? Sir, can we go to the next slide? Yeah, thank you. So this is the reference information from conventional network. So obviously, as we know that mostly we characterize the network traffic based on 3 KPIs, that is packet latency or delay, packet loss ratio, and packet delay variation. So these are the 3 important KPIs, and which gives us the characterization for the traffic on a certain network. And then we do see some traffic increments happening, and that happens due to the contention of the network native resources. Like we talk about cloud native resources. For the TSN, there is something called network native resources. So what is network native resources? So these are the resources in the network which ensures the SLA for the flows. And what are those resources? Like, for example, buffers, bandwidth, schedulers, and the policies, right? And of course, there are a few other things also, like your drop policy and all, right? So these are the network native resources. So, like, for example, the packet loss ratio, right? The packet loss can happen when there is a contention for the buffer. So important thing to note that whenever there is a contention for the network native resources, some kind of impairments can happen. When there is a contention for the buffer, then we lose the packet. And when there is a contention for the bandwidth, we will have more jitter, or we have a delay for the packet. Some of the packet delay and packet delay variations cannot be avoided. Those are intrinsic or random. Like, for example, arbiters in the packet process, right? Or quantization in the digital logic. So anytime you put the arbiters in the packet processing path, you induce certain level of delay or delay variance. Okay. So if I compare the conventional networking with the TSN, it's basically about the average performance and versus instantaneous performance. What I mean by average performance, so one practical example we normally see in the field that average utilization of link is only 5 gig for a 10 gig link, but we are still seeing the packet drop. But the question is that 5 gig has come during 1 second window, or it has come only during the 250 millisecond window, and then other 750 millisecond was idle. So if 5 gig is coming within the interval of 250 millisecond, that means we are already oversubscribing the link by 2x. So besides the buffers, right? So during that period, the buffer, the queue length will be increasing at the rate of 10 gig, right? And packet will start dropping once you exhaust all your buffer, right? Normally you have buffer for say 10 millisecond, 15 millisecond. Beyond that, you will start dropping the packet, right? So that's so average performance might look good, but the instantaneous performance will be bad, right? So TSN will try to focus on instantaneous performance. Conventional method of traffic management and the end-to-end traffic engineering is good enough for the average performance, but it's not good enough for instantaneous performance. Other thing is that offer load to the network. There should be a certain pattern. What you cannot measure cannot control, right? So we need, and what you can measure if there is a method in the traffic arrival pattern. So TSN also ensures that as the traffic is entering into the network, it has certain behavior. Sorry, some question?
No, please go on. It might be some disturbance.
Okay. Okay. So normally in the conventional network, the traffic arrival patterns are not so deterministic, right? So once it comes into the network, it has a possibility of destroying the SLA of some other flows also, right? So TSN will also provide methods to control the arrival pattern. So offer load to your network is emitting certain profile, and once it is emitting certain profile and you know a priori what is the profile, you can create a congestion-less path in the network if you want to. One important thing with the Ethernet networking is that it's asynchronous operation of different nodes. All nodes are independently working on its own time scale. There is no coordination between the nodes, right? And this is essentially a difference between the packet network and the TDM network, right? So in TDM, all the nodes are mostly synchronized, right? But in packet, that's not the case. So it works good. We all have, and it reduces the cost of the network because we have the statistical mux gain and make the node architecture a little bit easier. But then when it comes to meet the very low latency, high reliable service, then it falls short. And we'll see going forward in the slide that some of the methods of the TSNs will need the synchronous operation of all the nodes who are falling in the data path. Then there are two levels of coordination. One is the control plane level of coordination like RSVPT or path computation engine. You must have heard about it in the conventional network, but that will give you performance on a longer time scale. It doesn't have the capability to coordinate at the microsecond scale in the data plane. And that's where the TSN provides the method. So TSN will provide method which can coordinate at the microsecond level to ensure the traffic SLA. And one last important thing, normally in the conventional network, we talk about cross inference, like there are 8 classes of service and one service should not destroy the SLA for other service. But in TSN, it's more than that. Within the class of the service, like suppose there are 10 free flow in the front hall, right? So it should not so happen that 5 are going good and five of the flows are their SLA is getting destroyed, and they are not getting destroyed due to low priority traffic. They are getting destroyed due to the high priority traffic. That's called like self inference. So TSN will make sure that we'll have like multiple independent flows, and as long as the native resources of the network allows that, we'll be able to meet the SLA. So any question on this slide?
No, I think we can go ahead.
Okay.
Generally, we can take up questions at the end,
okay,
so that your flow is not disturbed.
Okay.
Should I go to the next slide?
Yes, please. Okay, so having talked about the conventional networking and its problem, so what TSN introduces, right, and how it makes the Ethernet to support the real-time or critical communication, right? So one important thing what it does is that it provides low and the bounded latency. Why we need the bounded latency? Because if you have a long tail, normal network will have a long tail. We'll see going forward 3-4 slides henceforth that if you have a long tail, then and if you still want to maintain the low packet loss, right, then you will have to over provision the network. And depending upon how extended that tail is, you have to keep provisioning the network, right? So that's why the low and the bounded latency is important. Low latency, like sometimes that's driven by the physics, like propagation delay or serialization delay on the link. That you cannot do anything. But this is when we talk about low latency here, the low latency induced by contention between the different flow on the same port on the same node. And then due to the cascaded multi-hop network, this impairment can add up, right? And eventually it will give you a bad matrix which doesn't meet the required mask. So for that, it has like time-aware scheduling, time-coordinated forwarding, and frame preemption. So first two are basically needed, will require the synchronized node. So and so that all nodes are working on the same time scale. So that means they are synchronized in time, and that's where the PTP equivalent protocol will be used to synchronize one node with the other node, right? So that they have the same reference of the time scale. And the frame preemption is basically to avoid the jitter, because if a high priority traffic comes and a lower priority traffic is already under transmission, as per the current Ethernet spec, you cannot interrupt that transmission. So suppose a jumbo frame 9K is on its way and only 5 bytes have been transmitted and a high priority traffic comes, then you have to wait for another 9,000 bytes of the packet before you can send your higher priority traffic. And that's where it induced delay and jitter. At the same time, since we are talking about URLs, you will see that as per the TS22.261, there are some of the very stringent requirement of the latency, right? Say 1 millisecond loop time. So if it is 1 millisecond loop time, you don't have opportunity to retransmit the packet, right? So then what you do? Obviously, their packet can get lost in the network due to, say, for example, CRC error, or you can get you can lose the packet on the air interface. obviously your interface is more vulnerable than the wired interface. Then what you do? So how we provide that reliability? Obviously, one method is that you send multiple copy of the same packet, so at least one out of many will get received at the destination. And then all this reliability and very critical SLA you can only ensure by reserving the resource. Then TSN also provides the capability so that flow can be removed or added without impacting other flow. It should not so happen that when I'm provisioning a new flow or setting up the new path, it is disturbing and destroying the SLA of some ongoing communication. And one important thing that we want to bring TSN to the Ethernet, and only reason for that is, and we are not going for a new protocol, is that we want to take advantage of economics of scale of Ethernet. Ethernet is all over the place, and obviously it's a widely used and understood technology. So we want to take advantage of that. That means TSN traffic can coexist with non-TSN traffic or not so critical traffic, right? And at higher utilization level, you can still get the performance at say 30% utilization level or 40% utilization level, but TSN performance as per the spec they want it. Sorry? Yeah. Any questions, sir? Okay. Okay, and TSN is being developed for Ethernet by a task group in IEEE 802.1, but this is for L2, right? 802.1 is L2, right? And TSN equivalent technology is being developed for L3 networking in IEEE, IETF TechNet work group. That's called deterministic networking. Okay, sir, we can go to the next slide. Can we? Okay, yeah. So as we discussed in the during last two slides, that Ethernet is asynchronous in the conventional way, and nodes are not synchronized, right? And at the same time, it is not deterministic. And one example which I have shown in this figure, that we are getting say 3 high priority packet, right? 3 red packets, right, which are high priority, and we are getting one big low priority traffic between packet number 2 and packet number 3. Then you can see that packet 1 and 2 went at the right time, but packet 3 got delayed due to the low priority traffic. This is called inference from the low priority traffic to the high priority flow. So you can see there is a variation induced in the inter-arrival time of the packets due to inference of the low priority traffic. And this problem will be solved by the frame preemption when we look into the TSN method of frame preemption. Okay, can we go to the next slide, sir? Yeah. So what is the basic concept? So obviously, as you have, by this time, there is enough hint that for some of the method and important method of TSN, we need to move to the synchronized networks. Like first of all the nodes needs to be synchronized. I mean, the sense of timing reference should be same. So when one node say it's 10 a.m., other node should also say 10 a.m. with a very minor error of say 1 microsecond or maybe less than a microsecond. Okay. And then we build a TDM-like method, like we define the cycle. Okay, from timeline X to Y, there is a cycle. And during this cycle, only the high priority traffic will be coming in. Okay. And we also need to create a guard band, right? It should not so happen that when I start that transmission cycle, there was a frame transmission going on during the last cycle, and that can interfere with the start of the this cycle. So we also want to create a guard band. Okay, guard band is basically keeping the link idle. So it's obviously waste of the resources. And so while we want to have guard band, we want to have a minimal guard band. And again, the frame preemption will help here, like that will minimize the guard band. We don't have to reserve the bandwidth for the maximum size packet. We only need to create guard band equivalent to 64 byte packet, 64 byte fragments, not like for 9K byte packet size. Okay, we can go to the next slide, sir. Okay, so this section basically, what are the important components for the TSN, right? So there are four pillars here. The synchronization, as we talked about, that different nodes need to be synchronized, and that 802.1s, which is a profile of PTP 1588. You must have heard about it, right? Then there is a bounded latency, most important one, and there are different methods. And most important methods in my view is 802.1BV, that's called time aware SEPA, and the frame preemption, that's 802.1AU and 802.3BR. And besides that, 1AB, so these two, so basically 802.1BV will need the time synchronization across the node. Similarly, like cyclic queuing and forwarding will need the synchronization across the node, but credit-based SEPA will not need the synchronization across the node. Frame preemption also will not require the synchronization across the node, right? So what I'm saying that it's not that all the TSN methods will need the synchronized operation, and at the same time, all the flows will also not need that critical SLA, right? So depending upon the criticality of the flow, you apply the right methods. Some of the methods will need the synchronization of the nodes. The reliability, basically 802.1CB, is basically frame replication and elimination. At the source, you replicate the frame n times on a diverse path, and then you eliminate at the destination, right? So that even if you lose one frame or more than one frame, then still you are getting the frame to the destination, and you don't have to fall back to the retransmission, because the kind of SLA which you'll be tracking for some of the use cases, you don't have the opportunity of retransmission. And then 802.CA and QCI, CA is basically how to set up the path. That's a control plane operation. And QCI is basically reliability in the sense that it will create a gate for admitting the traffic into the network. So basically, it filters out the traffic which is not conforming the certain profile. Whether the packet is arriving with a bigger packet size than what has been configured, or the rate of the arrival packet is higher, or some other anomaly. We have seen the list of we have captured the list of anomalies going forward in this slides, right? It's basically something similar to the polycell in the traditional network, which control the offered load to the network, but here checks are even more stringent, right? So it's not only the bandwidth-wise control; it's more than that. Packet size, packet inter-arrival time, packet burst, and many those kind of parameters. And the resource management, of course, we need to coordinate and orchestrate the network native resources in the data plane. And to be able to do that, we need a protocol and the methods in the control plane, so that multiple nodes you can view as a system, and then do the resource modeling, and then orchestrate the resource across the node, so that we have a right coordinated congestion-less path for critical TSN flow. Okay, we can move to the next slide, sir. Okay, so obviously what TSN is doing, it's making Ethernet more deterministic, and these are the formal definition of deterministic networking, in line with 802.1 TSN group and IEEE DETNet working group. So basically, for some of the flow performance, we need the time synchronization, we need the resource reservation, we should have method for extraordinarily low packet loss ratio. Normally, what happens that in carrier Ethernet, we have like packet error rate of 10 to the power minus 6, which maps to the 10 to the power minus 10 or 11 at the bit error rate. And we need a little bit more than this for some use cases. And that's where the TSN is important. And we talked about the reliability, right? So if we go use TAS and the reliability methods of the TSN, we may get the packet error rate, which is higher than 10 to the power minus 6. 10 to the minus 10 is a good number to have, but still I don't see anywhere we are able to meet it. It's basically mapped to 10 to the power minus 15 bit error rate. So even if we have these methods in the packet processors and the node, we still cannot guarantee this performance due to CRCs and things like that, a link error and those kind of things. So we'll try to reach, but we are not there yet. Then of course we talked about the granted end-to-end latency and with the normal traffic with the loading of 75% on the lane. We can go to the next slide, sir. Okay, so during the last few slides, we talked about bounded latency, and this is what it means. Normal service curve will have extended tail of the latency curve, and if you want to capture that tail to avoid the packet loss, two things will happen. First, you have to over provision the network, and the second thing that your jitter will increase. You can compensate the jitter, but if you're compensating the jitter, you have to buffer the packet, right? And if you buffer the packet, you increase the delay. So if you look at the 2 or 3 parameters, all are interrelated, right? If you want to meet the packet loss ratio, you are destroying the jitter and the packet delay parameter, right? So that's why we want to cut down of the tail latency of the latency curve, and that's what TSN methods will provide. So obviously, the tail latency will be much limited for the TSN engineered path in the network, right? So that's which we are showing at the bottom. Okay, we can go to the next slide, sir. Okay, so these are the as I told you during the start of this presentation, TSN is a collection of different methods, and all methods are being independently pursued in the different working group of a standard body, or even in so like you can see the list of different specs like QAV, QBU, QBV, QCH, and I have marked green, which will be focusing in this presentation. And some of them are already made to the standard, some of them are still being discussed, right? So this is a comprehensive list of the TSN standards, right? Towards the end, I also want to give you one more important information that TSN is a collection of methods, right? But in the IEEE, they also want to create a vertical use case. For example, which we are working very closely at 802.1cm. This is verticalization of this is a vertical use case for the CRAN application, the mobile 5G front haul or 4G front haul, right? Where we are packetized front haul, and to be able to support that on an Ethernet network, what are the TSN methods we need, right? So this is covered in 802.1cm. There are some other spec also for AVB and some other applications also, but we are connected with 802.1cm. So there are multiple verticals which are trying to create a profile that which TSN method you can use to meet the requirement, critical SLA for certain use cases, like front hauls, like audio video bridging, or professional media, or say for example, Industry 4.0 and things like that. Okay, we can go to the next slide, sir. Okay, next 3-4 slides will be basically trying to establish a context between the 5G valency and the TSN. So this is directly from the spec. I have given the reference to 2.261, table 7.2.1, and you can see the latency, the availability, and the reliability numbers here, right? important thing to note here that is, as I was telling earlier also, that it's not that all of the use cases will need a very low latency. Maybe some of them will not need it, and for that you don't have to put very stringent TSN method. But for those who needs it, you have to, right? Similarly, you can see like the availability and the reliability, right? So that's also very high. For example, the discrete automation, your end-to-end latency is 1 millisecond, reliability is like 10 to the power minus 5, 6, something like that, right? So and why this table I put, because this put the demand on the air interface as well as on the transport network. Okay, and then we have 5G 3GPP already developing the air interface in that line, right? And Ethernet, which is the transport network part of the 5G system, also need to do the impedance matching. So this is a little bit details. There are more methods, could be more methods for meeting the low latency and reliability on the 5G air interface, but I have captured some of the things which I could understand, right? So like for low latency, in LTE, you know that like 20 megahertz bandwidth, we had like 15 kilohertz subcarrier spacing. So that maps to 66.67 WebDM symbol length, right? And then you have like 1 millisecond of TTI frame, 0.5 millisecond of subframes, and that means 14 such WebDM symbols in one radio frame. But obviously, you can see that delay induced due to WebDM symbol length and also the jitter. Like suppose we used to process, in LTE you used to process like one subframe at a time, right? That means you can introduce the jitter from 0 to 500 microseconds because one length of that subframe is 500 microseconds. So one thing what is happening in 5G that you are bringing down, this is a flexible numerology, right? So at the physical layer level, right? So you can go for higher subcarrier space, like from 15 kilohertz, you can go to 30 kilohertz, 60 kilohertz, even 120 kilohertz. And then if you are using 120 kilohertz, that means you are bringing down the TTI length from 1 millisecond to 0.125 millisecond. That means you are reducing the symbol time by 8, you are reducing the frame size by 8. So already you are reducing the latency by 8, right? Similarly, in LTE, we schedule at the in a bunch of phase on a slot like 1 millisecond, right? In 5G, we can define a mini slot, and that you can schedule independently, right? So that your scheduling latency also come down. So there are in LTE you also ask for the uplink grant before you send the packet. In 5G there is a method where you can fix certain slot, right, where you don't have to ask for the grant, right? That you can always use that slot to send the data, right? So these are some of the enhancements they have done at the air interface level. Reliability wise, as I was telling, that there can be n number of packets being replicated, right? And then one will make eventually to the destination. See, in the non-public network, like in a private location-specific use case, say factory floor, right? Two most important technology from 5G is the millimeter wave spectrum and the edge computing, right? But the millimeter wave spectrum has a very bad path loss characteristics, right? So to be able to provide more reliability, what we need is a cooperative MIMO. So basically what happens that you radiate the waveform from two different antennas, and so that when it reaches at the destination, you have the addition of those RF energy so that the signal quality is supposed to be better, right? So yeah, so there are methods for reliability also. So point I'm trying to make here is that 5G is already taken care at the air interface level, something similar and in line to support the low latency, low jitter and reliable services. And this needs to be supported and impedance matched by the transport network, which is basically Ethernet today. Can we go to the next slide? Okay, so here I try to compare that different methods in the air interface and the equivalent TSN methods, and you can see there's a perfect impedance match, right, between the air interface and the Ethernet, and that's so it so it establishes a context or relevance for the TSN with respect to the 5G URLC use case. One use case which I'm trying to say, which is most important, most challenging to.
Excuse me, sir. Hello.
Sorry. Yeah, go ahead.
Sorry for the interruption, sir. Sir, we are not able to show your screen, sir. The screen are not shared to us.
Sir,
we are not getting the slides, sir.
Okay, so no, I myself is not sharing it. Rajput sir is doing that for me, right? So. I don't know.
I think I can see the screen, Prashant sir.
Yeah.
I'm able to see the screen. I'm assuming that maybe a problem at one specific end.
You are able to see the slide, Chris?
Yes, I am able to see the slides.
Like TSN and 5G I'm showing right now, right?
Yes, impedance match between air interface and TSN.
Okay, so Girish, I think Rajput sir has to make do whatever he can do, because I'm not sharing. I also could not share it, right? I didn't get the control. So can you talk to him, please?
Hey, guys, anyone else is not able to see? Can you just speak out?
Sir, attendees are not able.
Attendees are not able to see?
Sir, your screen is not shared. We are not able to see the screen.
Okay. So maybe just hold on for a minute. Maybe I'll, Dr. Rajput, or are you there? Let me see. Just give a minute. We'll take a pause for 2 minutes and probably meanwhile I'll see how I can help.
my
कुछ लोग मतलब देख नहीं पा रहे हैं जबकि
नहीं they might be on a slow network because it is very visible.
So now the screen is visible.
Now it's visible.
We did not do anything. Actually, it might be because of the slow internet on your end, because we are also streaming it on the YouTube, and on YouTube we are able to see it perfectly well, right? So that means so it may be because of some speed glitch. Okay, but you will see it.
Yes, sir. No, sir. Thank you.
Please go on.
Yeah.
Okay, so yeah, this slide, as we were discussing in the last slide, that 5G URLC case, the air interface is evolving in line with the TSN, and so 5G not about only about the air interface. 5G systems, if you look at the specs, they call it 5GS. 5G system is a combination of three things, right? Air interface, transport network, and the 5G core, right? So if air interface is providing methods for meeting the reliability and the low latency services, that should impedance match with the transport network, and that's primarily Ethernet nowadays. So Ethernet should have capability to do the impedance matching so that we have the end-to-end performance for the reliability and the low latency, right? This is what is being covered in this slide. Okay, so I have tried to map the different TSN methods with the relevant part of the air interface. Yeah. Okay, can we go to the next slide, sir? Okay. So as we were talking during last few slides, right? For the non-public network, for say for example, location specific industry 4.0 factory floor, right? One of the most important technology is the edge computing and the microwave spectrum. Microwave spectrum being very high frequency, obviously it can go to a limited distance, right? And also its path loss characteristics are also not very good. So to make sure that we have the good reliability in the RF communication, what happens that the same data gets communicated from the different antennas, right? So So when the same data is being transmitted from the different antenna, they should be aligned in the time domain. They should be aligned with respect to the timing. Otherwise, there is an offset between the two. Then instead of creating a constructive inference, it may create a destructive inference, right? So, if you consider it from the frontbound perspective, the CRAN, where all the radio is being centralized, radio logic is being centralized to the most of the radio logic is being centralized at the one central location, right? But still, the distance between the different transmission antenna from that CRAN hub or disband unit, which what we call it DU in the ORAN, right, is different. So that means TSN method should make sure that those packets are being delivered at the right time, so that there is a constructive inference at the UE level when it's coming from the different when the different beam is coming from the different antenna. Okay, we can go to the next slide, sir. Okay, so okay, so this is basically synchronization overview, and this will be needed for synchronizing the network. I mean, from every node should have the sense of the same time scale, right? And this is basically how you pass the timing based in a packet network. So here I have shown, like, it's a basic information, the frequency synchronization, the phase synchronization, but important thing is the time synchronization, right? That's what will be important from the TSN perspective. So like every phase will have the same notion of the time. Like, for example, node A say that it's 1 o'clock. That means node B also says it's 1 o'clock right now, right? So once you phase time synchronized, anyway, you are phase and frequency synchronized. Right. We can go to the next slide, sir. Okay, so obviously at the start, the two nodes will not have the same timing, right? And there is a time error, and there are different component of this time error, right? One is like constant time error, which is basically offset between the two nodes timing, right? The second one is the frequency offset. Both are being clocked by the different frequency. Oscillators are being used, which are having slight difference. Even if we say like 8 kilohertz oscillator, still there will be slight ppm difference, right? Then over a period of time, there will be a frequency drift, right? And the rate of drift is also not fixed for the different nodes, right? And then there is some random variations, right? So this time synchronization protocol will take care of all of this, right? So like, for example, it will try to eradicate the constant time error. It will try to take out the frequency offset. It will try to take out the frequency drift by repeatedly doing the measurement. And the random variation will be taken out by the filter. Since it's a AC, so AC equivalent, so that means you'll be able to filter out and give a DC component of it and set your timing circuits such that there's not much dynamic time error. We can go to the next slide, sir. Okay, so this is basically how to take out the constant time offset, right? So most important thing for this is that you need to precisely timestamp the outgoing packet and the incoming packet. And as per the standard, more closer to the offset, more closer to the physical layer you do it, more accurate your clock synchronization will be. And it will be aligned with the SFD, the start of the frame delimiter for the Ethernet, and it should be done very close to the file layer, right? If there is an inaccuracy for the time stamping, that will always show off as a constant time offset error. Other assumption here is that propagation delay between node A to node B is symmetric. If that is asymmetric, then there's again an offset error will be created. Okay, and this is basically frequency offset. So obviously we do this measurement over a period of time, and we can see that, okay, node A has moved from this much from T1 to T2, but node B has only moved from little less or little more than that, right? And when we map it to the frequency error, we'll be able to find out the ppm, the part per million error. So here in this example, what I'm saying that assuming that we have a symmetric link delay of 10, right? So what we are getting is basically the ratio. If the ratio is 1, that means the frequency offset is 0. But if ratio is not 1, either we are running faster or slower than the peer node frequency. Here in the given example, it's 0.998. That means never is slow by 2000 ppm. So you have to use this value and change your timing circuit parameters so that your PLL clock a little bit faster, so that we come at par with our peer node. And we have to keep doing it repeatedly so that if there is a drift of the frequency over a period of time due to the temperature change, humidity change, or pressure change, your frequency oscillator characteristics will change, right? So by repeated measurement, we'll be able to keep that aligned with the peer node. Okay. Okay, we can go to the next one. Okay, so now this section basically covers the frame preemption and interspace traffic. It's basically two spec 802.1QAU and 802.3BR. 802.1QAU is basically fragmenting the interrupting the ongoing transmission and create fragments of the lower priority traffic, and the 802.3BR is how to support that at the physical layer. So from this slide, right, what I'm trying to say that there is already an interfering frame, and then a bunch of packets comes like high priority. The yellow one is the high priority traffic, but it has to wait because there is already a transmission going on. So due to this, suppose it's a 500 byte low priority packet and it's 1 gig link, then what we'll have like on a 10 gig link, we'll have like a delay of 1.7 microsecond, right? So 1.7 microsecond, the high priority traffic has to wait, right? So what 802. What frame preemption provides is basically you can frame the traffic, you can frame the transmission of ongoing low priority traffic, and you can start sending your high priority traffic. And once your high priority traffic is sent, then you can resume and send the rest of the data. That means you are fragmenting the low priority traffic. You are fragmenting and reassembling at the peer node. Okay, we can go to the next slide, sir. So it's basically paraphrasing the same what we discussed in the last slide. So when the express, so basically we call it the high priority packet, we call it express frame. So when express frame arrives, the low priority traffic transmission will be halted, and high priority traffic will be sent, and then the low priority traffic will resume its transmission, right? And it will be these fragments will be reassembled at the remote end to create the original low priority frame. So that's how we reduce the jitter induced by the low priority frame into a high priority traffic stream. Okay, so we can go to the next slide. Yeah. So this is other part of the frame preemption, and this gives the specification for, we talked about the fragmentation and reassembly. That's good at the L2 level, but eventually that has to go on the physical layer, right? So this basically drives that what can be the minimal fragment size. Like as you can see, like minimal fragment size is 64 bytes. Then what should be the SFD, and for the express frame, what should be the SFD for the preempted frame, what should be the SFD for the intermediate fragment, what should be the SFD for the start of the fragment. All these things will be driven by this spec. And how do you discover this capability? So that means LLDP, so link level discovery protocol. This is another protocol which runs between the two peer nodes, and it will have definition of new TLB, and based on that it will discover the capability of the peer node, whether it supports the fragmentation or not, or preemption or not, right? Based on that, you can configure your local side that, okay, you can configure the frame preemption or not. If the peer node doesn't support, you cannot configure, right? Okay, we can go to the next slide. Okay, so this is most important part of the TSN, right? Because it controls the the behavior of the flow. Like, it makes sure that there is no burst and the flow is scheduled, the packet is scheduled at the right time, so that the preceding node exactly knows that when the packet is going to arrive. So there is no uncertainty here. So if there is no uncertainty, so you can allocate the resource with confidence, and at the same time it doesn't create challenge for some other flows, right? So it doesn't destroy, it honors its own SLA, it honors the other SLA as well. This method will need the time synchronization between the nodes, so it is a little bit costly and a little bit complicated to implement, but this gives the maximal performance for the critical flows, for the low latency and the reliability. And what happens that there are different queues, and all will have like gate whether you are on and off. If you are on, if that gate is on, that means that queue is allowed to send the data. If that queue is off, that gate is off, that queue is not allowed to send the data. And this on and off is coordinated based on synchronized timing. So suppose there are 3 nodes, so you can configure that when the gate for the queue number 1 will get open, right? When the on node 1, when the gate for the queue number 1 will open on node 2, when the gate for the queue number 1 will open on the node 3. So this synchronization makes sure that when the packet starts from node 1 and reaches node 2, it will hit an open gate, right? That way it will not it will not have waiting time or undetermined waiting time and pick up the noise in form of jitter, right? So it has a congestion loss path set up in a multi-hop network. Okay, so next slide, sir. Okay, so there are 2-3 other important methods. So like ingress policing. So this basically to avoid the control the offer load to the network to avoid the DOS attack or erroneous delivery equipment failure, right? So it basically analyze the different parameters and decide whether I should admit this packet or not. So of course, one traditional and conventional wisdom is that policing based on the bandwidth usage, that even today the MEF policer and other policer, ITF policer does that. Then it also uses like burst size, the packet size, and it also uses like inter-arrival time, right? If the packets are arriving too fast, inter-arrival time is varying more than what it should be. That's where it will get captured in the threshold counter, right? So that if it happens like that, then it creates problem for SLA of some other critical flow. That's where this ingress policing is used. And so it's basically a method to ensure more reliability to the flow, so that unrelated flows cannot impact other flows, right? So yeah, we can go to the next slide, sir. Okay, so this is basically for reliability. So what happens that at the source node, we replicate the packet on the multiple path, disjoint path, and eventually those packets are replicated with a certain sequence number. And at the final node, we receive those packets. Most of the time, we'll receive both copy of the packet or n number of. If I replicating n times, I will get like n packets, right? And I will pass only one and drop all other packet of the same sequence number. Like in this case, like sequence number 14 arrives to the N2 node, and if both copies arrives, I will pass only one and drop other. So this is basically frame replication and elimination method for hitting the reliability. Okay, sir, we can go to the next slide. Okay, and this cyclic forwarding is basically what happens that is a you collect the certain number of frame in one cycle and release in the next cycle. So here you have a notion of cycle that is again synchronized with respect to the timing, right? And then what happens that one node transmit in one cycle, other node collect in its cycle, and then transmit into the next cycle. That way, it's a cyclic forwarding, right? Collect and release, collect and release. So it's very synchronized, and it keeps the rather than dealing it at a packet level, you have amortize the complexity by using it for a bunch of packet. Okay, so you can go to the next slide. Yeah. So this is basically end-to-end view of a TSN path setup. So obviously, you can see there are two parts of this network. One is the user nodes, like robots and the controller in the factory floor, and then you have a bridge edge L2 network, TSN network, right? And then we have like two controllers. One is that the centralized user configuration, which basically and then we have like centralized network configuration, and these two controllers can configure the different parameters in the end-to-end path. And what are those parameters? Depending upon what kind of SLA you need, it could be like credit-based shaper algorithm, frame preemption, scheduled traffic. That's basically 802.1 QBB, the time-aware shaper. Or if you need reliability, it will be able to configure your frame replication and elimination for reliability. Per stream filtering and policy for reliability and avoiding the DDoS attack or any equipment failure, and the cyclic queuing and forwarding for the more latency and deterministic forwarding across the different nodes. So that's all I had, sir, today. Almost 3 minutes before. We can take the question for next few minutes, sir.
Yes, now we can take up some questions. Yeah, dear participants, you can raise some questions if you have some queries.
Sir, as we are talking about 5G technologies and the microwaves we are using, very highly microwaves we are using, sir, is there any impact on the environment of that uses? Any impact on the lives?
Any impact on that? I don't know, man. What the impact of 5G spectrum on the human, that I don't know. I keep hearing something, but I don't have any information on that.
Actually, this is beyond our current prerogatives. We are not here to discuss that effect, right? Although environmentalists and other people, they are of course might be researching the effects, right? So it is not the right platform to make a comment on that. But however,
I just want to know the sustainability of this technology.
Technology is sustainable, of course. In fact, this is the need of the hour. If you have to comply with the industry 4 standards, right? And if you really want to come up with industry grade effective cyber physical systems which will be able to control the complete industrial process in real time, right? The packet delivery constraints and other things are very important, right?
Yes, sir.
Okay, I think other participants don't have additional questions, so I think we can. But Prashant, I just had one question. Right now, our transport protocols are best effort delivery services, right? And we still have packet loss. in some of the literature when I was going through, they said that now we need a guaranteed packet delivery service. So would it still be best effort with very low packet loss, or there would still be technological scope of packet loss?
Okay, so as we were discussing during this presentation, sir, that there are multiple methods in the TSN. So if you want to set up first of all, you'll be able to set up a zero congestion path. So you lose the packet due to the congestion, right? When there is a contention for a certain resource, so you will be able to set up the zero. But then if you are able to set it up for all the flow, that means you are turning your packet network to the TDM network, right? And that means you are losing all the benefit of the packet network of the stat max and all. So here we in the TSN, using TSN method, we will be able to set up a zero congestion path for some of the flow. And if we are able to set it up, then there will not be a loss due to congestion. There can be a loss on the physical layer due to the CRC errors, or say there can be a loss due to RF on the RF side, but not due to the congestion, right? And so avoid that error, what we can do that we can replicate the packet on the two different diverse paths, so that probability of that error is also becoming less. It is very unlikely that same packet getting dropped, at this when I'm transmitting it to the different path, right? So that's where the this method comes in. Like you provide the zero congestion path, and you provide the replication of the packet to the different diverse path, right? So that you have the very reliable communication and low latency communication.
Right. So Anand, do you think that we will be able to bring TSN on actual real field applications maybe soon, or for example, for a small sensor node at the laboratory setup level? Can we currently right now are able to do some tweaking on the network performance so that near real-time deliveries are possible at laboratory level, and even students or people, faculty members like us, who just want to have first feel of this TSN system, can we implement it at laboratory level using open source hardware platforms like Raspberry Pi, or some microcontrollers like Arduino or ESP32 kind of smaller systems?
Yeah, so I'm not quite sure about the Raspberry Pi and all, right? Because these are, like, for example, as I told, like the three most important part of the TSN, that the time synchronization, the frame preemption, and the time-aware saving. These are very complicated methods, right? And it has to be, so it cannot be done on the smaller.
So for the sake of demonstration before the students in my own laboratory for my research scholars, we have to wait for some more time when DIYs and smaller system the layouts would come up.
Yes, I think so.
Right. Okay. So Prashant, it had been a wonderful session. In fact, the participants have been exposed to such stringent requirements in a very systematic way, in a very structured manner. And in fact, we are also very thankful to have that you people have agreed to allow us to record the YouTube session, so that students can later on watch it again, pause the videos, explore it more, because this is the purest knowledge on TSN. Or in fact, I have been observing that other talks are also so pinpointed and in-depth that in fact a participant cannot just watch the program, rather he will have to pause, explore it further, understand it well, so that he develops a complete understanding of the subject matter. So we are really thankful. So Ajay, are you there?
I am here.
Yeah. Okay. So I will request my co-coordinator Ajay to please extend our deepest and sincere most vote of thanks to Ajay and to Prashant. So Ajay, please go on.
Okay. Thank you so much, Prashant, for taking a slot available for us, first of all, from your busy schedule. Okay, and giving such a nice elaborative presentation and giving us some more insight into knowing the topic. I hope many of us, including the audience, will get the opportunity to work, and maybe later on they will get opportunity to email you if they have any doubt. And for the new technology, sometimes it creates problem to understand in first shot itself. So if they will look into it for one or two more times, most probably they will get to know what actually going on in the backend. So thank you so much, and I hope in the future as well you will give opportunity to us. Maybe physically we'll invite you at IIT VHU campus, right? And big round of applause from our side. Thank you so much.
Thank you.
Thanks, sir. Thanks. It was my pleasure working with you.
Thank you so much. Bye bye.
Thanks.